Dear students, in the last class, so we have discussed all the theory related to simple harmonic motion. So we have derived expression for displacement, from which we derived expression for velocity, acceleration, force, potential energy, kinetic energy, and the total energy. Now, based on this theory, we will learn more about the simple harmonic motion, and I am going to derive an expression for time period of oscillation of a simple pendulum. Time period of oscillation of a simple pendulum. So we are going to consider a simple pendulum, a pendulum bob, which is suspended by a string of length L. This bob has a mass, and so its weight is mg, acts in the downward direction. Since it is suspended by a string, another force acts in the upward direction, which is called the tension in the string. So these two forces, they are equal and opposite. So the net force on the pendulum is 0. So pendulum remains at rest. Now we are going to displace this pendulum a side like this. Here. The same pendulum is displaced. So when displaced, let it displaced through a distance x, and that x is very small, so that this theta becomes very small, and L is the length, which is still here. So we can find the relation between theta, x, and L. So this is arc length. This is arc length, which is x. Then we have theta here, which is the angle, and this acts as the radius of the arc. So that what is the relation between the arc length, the angle, and the radius of the arc? So we know S is equal to r theta format, correct? S is equal to r into theta. So based on that, here S is nothing but x, and r is nothing but L, and then theta is that angle subtended. So this is one of the equation. X is equal to L into theta. Now the weight still acts in the downward direction, which is mg, and now the tension will be like this, which always acts towards the fixed point. And I will resolve this now vector into components. So if this is a theta, this angle is also theta, which is a corresponding angle. So if this is mg, so this component will be mg cos theta, and here the exactly perpendicular, which is mg sin theta. So it is this mg sin theta which helps the pendulum to come back to the mean position, because when the pendulum oscillates, it goes to the extreme position and it comes back. So what makes that pendulum to come back? That is because there is a force acts. This is the restoring force. So mg sin theta is the restoring force, mg sin theta. And what is the formula for that restoring force? We also know that the restoring force is given by F is equal to minus m omega square and x. Okay, yesterday we have derived it. F is equal to minus m omega square. I have given it as in the form of a y, but here the displacement I have taken it as x, so that's why F is equal to minus m omega square x. That is, F is equal to minus m omega square. We know x from here. X is nothing but L into theta. So this is the restoring force. The restoring force is also given by F is equal to mg sine theta. But since theta is very small, sine theta is approximated to theta. Sine theta is approximated to theta. And since it is again the restoring force, so we make use of the minus sign. So F is equal to minus mg theta. So here we have two equations for the restoring force. One is minus mg theta, the other is minus m omega square L theta. So equate them. So minus mg theta is equal to minus m omega square L into theta. So m theta will get cancelled. Minus minus becomes a plus, and what is left here is a g divided by L is equal to omega square. So from this, what is omega? Omega is equal to root of L by, g by L. G by L. But we wanted expression for time period, correct? So what is omega is equal to? Omega is nothing but 2 pi by t. Omega is 2 pi by t, that's equal to root of g by L. So take the reciprocal of that. T by 2 pi is equal to root of L by g. So therefore, final expression T is equal to 2 pi root of L by g. So this is the expression which we have already come across, in chapter units and measurement. So this is the expression for time period of oscillation of a simple pendulum. T is equal to 2 pi root of L by g. And time period is independent of the mass of the bob. It doesn't depend on the mass of the bob. And time period, it varies inversely as a g. Now on the moon, what is the time period? Is it same as that on the earth? The answer is no. It is on the moon, the value of g is lesser, correct? On the moon, the value of g is less. So that means the time period of oscillation is more on the moon. So like this, we can find the time period. If you want the expression for the frequency of the oscillation of the pendulum, then take the reciprocal of it. So how to find the frequency of the oscillation? F is equal to 1 by t. So we get 1 by 2 pi root of g by L. So this is the expression for frequency of oscillation of a simple pendulum. So time period of oscillation, frequency of oscillation, and then t is equal to 2 pi root of L by g. And then we can even find omega, which is equal to 2 pi f is nothing but omega, which is root of g by L. So these are the different equations related to oscillation of a simple pendulum. In a similar manner, we can even find the time period of oscillation of a oscillating spring or a block. So there is a spring, and this is the surface, and here there is a block of mass m. K is the spring constant. So this is a spring suspended, and here there is a block, which is m. So here, if the block is pulled like this, so this is the mean position. If the block is pulled and if it is left, then it oscillates about the mean position horizontally. So we can find the time period of oscillation of a block, which is a t is equal to 2 pi root of x by g, or that is also equal to 2 pi root of m by k. So there are two equations are there. One, t is equal to 2 pi root of x by g. What is x? X is the, so when you stretch it, so there will be elongation, correct? So x will be the stretch or elongation of the spring. G is the acceleration due to gravity. M by K. What is M? M is the mass of the block and K is the spring constant. So, time period of oscillation of a simple pendulum, is independent of the mass of the block, mass of the pendulum, whereas time period of oscillation of a spring connected to a block depends on the mass of the block. Time period of oscillation of a pendulum is independent of the mass, whereas here it depends on the mass of the block. Greater the mass, more is the time period of oscillation. How to write expression for frequency? F is equal to 1 by 2 pi root of G by X, that's equal to 1 by 2 pi root of K by M, which you can even write like this. If I multiply 2 pi, I'll get omega, because 2 pi F is omega. So, omega is equal to root of K by M. So, all these equations are related to time period of oscillation of a spring block system. So, we do have numericals based on all these topics, that is based on the equations which we derived yesterday, as well as based on the time period of oscillation of a pendulum and the time period of oscillation of a spring. So, we have a few numericals which I am going to solve in the next session.